Forces keep things moving, says Aristotle. You're wrong. Forces make things stop or change their direction. Inertia keeps things moving. Inertia, remember, being the reluctance of an object to change its motion. We're going to continue looking at inertia, how lazy can you be, with page 11. And we are going to return to page 10, letter G, the question about the pebble being swung around or the marble going around the life on the edge activity from carnival days. First, though, we are going to look at letter H. What is the above law called? Every object continues in a state of rest or of motion in a straight line at a constant speed unless it is compelled to change that state by force exerted upon it. That is known as the law of inertia, and Galileo is the one who developed this physics concept, which is often known as the first law of physics. More specifically, the first law of physics when it relates to motion. Looking at page 3 of your study guide, we have Sir Isaac Newton's 3 laws of motion. In that quite poisonous Beekman's World Song of Inertia, they mention Sir Isaac Newton, and that is because Sir Isaac Newton's first law of motion is really restating Galileo's law of inertia. So the first law of motion, law of inertia. This right here is key terms to help you remember the first law of motion. And this is why we have Galileo featured here on the page along with Sir Isaac Newton, even though it's Newton's laws of motion. Where Galileo left off, Newton essentially picked up, and maybe transcendentally in the sense that when Galileo passed away, Sir Isaac Newton was born. All right, without turning back to page 11, see how much of Galileo's law of inertia you can recall here. And extremely well done if you remembered something along the lines that every object is going to continue in motion or a straight line motion unless acted upon by some sort of outside force. We're going to go to the classic professors of Hume and Ivy, who I believe it was the 60s, put together some great physics clips that are just as relevant today for you. The one they're going to show you is one to hopefully convince you that objects do indeed travel in a straight line unless an outside force acts on it. So they're going to show you this hockey puck, they'll call it, and it's on this near frictionless table, meaning that this hockey puck is probably riding a little bit of air pocket there and is able to travel very nicely across this smooth surface. Again, watch this clip in terms of thinking about, okay, objects move in a straight line motion. Objects move in a straight line unless acted upon by some outside force.
What's happening this time? Why doesn't the puck move straight across the table as it did before? As you can see, it doesn't. So, if we believe in the law of inertia, then we must believe that there is an unbalanced force to change the velocity of the puck. But this puck is nearly frictionless. So what can be exerting this unbalanced force on it? Suppose that you watch the motion, this time, through a camera which is fixed in the Earth's frame of reference.
Ooh. Very clever. Can't really make my whole classroom spin for you.
I think if you concentrate on watching just the puck, you can see that it is moving in a straight line, and that therefore there is no unbalanced force acting on it.
Well, what do you know?
Now we're going to stop this rotation so that I can talk to you about what is happening here.
And puke. So we have the puck indeed moving in a straight line motion. It was just the table underneath that was moving. Let's think back to the pebble being swung by a string here, and then it breaks. Is it going to travel in direction A, B, C, or D? And the answer is C. Objects are always moving in a straight line motion, unless acted upon by some outside force. So as you're holding on to the pebble and swinging it round and round and round, it really is moving in a straight line. It's natural motion. And as soon as that outside force, the string that was keeping it in the circular path, is gone, it's going to keep on doing what it was already doing, which was moving in a straight line motion. This is just the same as with the paper plate from the Carnival Days Life on the Edge. And we're going to show that clip to you again of the marble going around the 3/4 plate. You'll see the marbles put into the plate in a straight line motion. And it does travel around the plate in a straight line motion. Once that outside force is no longer pushing on that marble, it goes back to doing what it already was doing. Rather, I should say, it keeps on doing what it was already doing. It was moving in a straight line. We perceive it as a curved path because that force by the plate to push it as it goes around the plate. But really, if you think about it, that marble is moving in a straight line the entire time. Similarly, perhaps I'm in a car and this is the dashboard and the pen on the dashboard. You're driving forward. The pen is sitting on the top of the dash part of the car. It wants to keep on moving forward, and it does. Let's say you make a left turn though. Take a left turn. It appears as though that pen slides away from you. But if you think about it, the pen is continuing to move forward. It's the car underneath that's doing the turning and moving away. That pen keeps moving forward, 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 forward. As the car turns, we perceive it as sliding, like we perceive the marble going around in the cup as a curve, but it's actually the pen, the coins moving forward because of inertia. They keep on doing what they're already doing. Inertia. We have the rock, pebble, marble, coins on a dashboard. They're moving in a straight line motion, and we perceive that curvature because of this outside force pulling on that rock in this particular situation. As soon as that outside force is gone, the rock continues to move in a straight line motion. A question that is often asked on learning logs in class would be, what happens if the earth suddenly stops spinning? Well, you would die. I mean, that's all there is to it. You die. There's no escaping. You can't be flying up here 30,000 feet above the earth. You're still under the influence. But moving past the you die part, if Earth were to suddenly stop spinning, inertia would cause everything, including ocean water, to jerk sideways at 1,600 kilometers per hour. And if you don't believe me, take NDT, Dr. Neil deGrasse Tyson's word for it.
Johnny Basher via Twitter wants to know what would happen if the Earth stopped rotating for a second.
Oh, yeah, that would be disastrous. Disastrous, because right now, here in New York, you can calculate at our latitude, we are all moving with the Earth at 800 miles an hour, due east, because Earth is rotating. If you stopped Earth and you weren't seat belt buckled to the Earth, you would fall over and roll 800 miles an hour due east. It would kill everyone on Earth. People would be flying out of windows, and that would just be a bad day on Earth. I'm just saying.
All right, continuing on page 11, letter I. Describe how Galileo came to this understanding. Well, I've taken this image from Paul Hewitt textbook and paused the video and read through the explanation here and the description of the images A, B, and C here to the left. And don't just jot down this into your notes, otherwise I'd have printed it in for you. What you're doing is reading through these texts and then putting it into words that's most useful for you to answer the question how Galileo came to this understanding meaning the law of inertia. So pause the video here, read through this, and use your phrasing to describe how Galileo developed the law of inertia. Letter J. What do unbalanced forces cause? This is a huge concept for this study guide and for physics in general. Huge concept right here, letter J. What do unbalanced forces cause? Well, unbalanced forces cause acceleration, which at the start of this unit I told you that's the overriding theme here, acceleration. And absolutely vital is understanding that unbalanced forces result in acceleration. Letter K. Explain why zero acceleration does not just mean no motion. We looked at this earlier with either the pen stroke moving across the grid at 1 square rectangle per second, or in the classroom, my walking at 1 tile per second. So this is a repeat question from earlier, but I want to emphasize it even further because it is so pivotal to understanding acceleration. We are going to look at this chart, but before we look at this diagram here, we're going to turn to Professor Human Ivy to show you exactly what we mean by zero acceleration, just not meaning no motion.
We are used to seeing things from a particular point of view, that is, from a particular frame of reference. And things look different to us under different circumstances. At the moment, things look You look peculiar. You're upside down. No, you're the one that's upside down. No, you're upside down. No, I'm not. He's the one that's upside down, isn't he? Well, let's toss for it. All right. Okay. You lose. He's the one that's really upside down. You better come into my frame of reference now. My frame of reference was inverted from what it usually is. That view of things would be normal for me if I normally walked on my hands. This represents a frame of reference, just 3 rods stuck together so that each is at right angles to the other 2. Now I'm going to move in this direction. You see the frame at the same spot on your screen, but you know I'm moving this way because you see the wall moving this way behind me. But how do you know that I'm not standing still and the wall moving? It was the wall that was moving. Now the wall has disappeared, and you have no way of telling whether I am moving or not. But now you know that I'm moving. The point of this is that all motion is relative. In both cases, I was moving relative to the wall, and the wall was moving relative to me. All motion is relative, but we tend to think of one thing as being fixed and the other thing as being moving. We usually think of the earth as fixed, and walls are usually fixed to the earth, so perhaps you were surprised the first time when it was the wall that was moving and not Dr. Hume. A frame of reference fixed to the earth is the most common frame of reference in which to observe the motion of other things.
As mentioned, this isn't a new concept, the idea that an object with zero acceleration doesn't necessarily mean just no motion. This is something we addressed at the beginning of this unit with page 4, letter F. Describe the velocity of an object when its acceleration is zero. And this is where we did either online in the video, the 1 grid line per second, or in class, my walking 1 tile per second. So back to the diagram on page 11. When we have forces that are in balance, we do not have acceleration. As you recall, unbalanced forces are what cause acceleration. So if my forces are in balance, we have two options. The most commonly thought of option is that an object is at rest with no acceleration, an acceleration of 0 meters per second per second. So velocity is 0. But one of the concepts we're trying to introduce to you with this study guide is that you can have objects in motion with 0 acceleration. And those are the objects that are moving along in a straight line. So they're not changing direction. They're not having an increase in velocity that's timed, nor are they having a decrease in velocity that is timed. So an object that has 0 acceleration can be not moving, but it also can be moving as it stays in motion at that constant velocity, that inertia, the reluctance of an object to change its motion, that every object continues in a straight line motion unless acted upon by some outside force, as unbalanced forces cause acceleration. Letter L. A 4 kilogram object is moving across a frictionless surface. Of course, there's nowhere that exists a frictionless surface, but with a constant velocity of 2 meters per second east. Which one of the following horizontal forces is necessary to maintain this state of motion? A, 0 newtons, B, 8 newtons, C, 80 newtons, D depends on the initial force. We just want to remind you, Newton from Physics A, it's your SI unit of force. Now we were looking at electrical force with Coulomb's law, the electrical force being measured in newtons. We're still talking about forces, and so the SI unit of force is the Newton. And just to refresh the memory as well, a force of 1 Newton is what it would be like to hold about a standard average apple in your hand. That force the apple's exerting on your hand, or your hand exerting upward on the apple, holding it in your hand, that's about 1 Newton of force. Because no force is required to keep an object in motion, the answer to letter L, the answer is A. No amount of force is necessary to maintain the motion of moving along at 2 meters east. So 2 meters per second east. So this is an example here of an object that is in motion will stay in motion, particularly this key word thrown at you here of frictionless. So no amount of force is necessary to keep an object moving. That is that vast difference between the way the Greeks and the Galilean way of describing motion differ. And Galileo having the correct mindset for describing objects maintaining their current state of motion. Letter M. The law of inertia states no force is required to maintain motion. Very true. So why do you have to keep pedaling to maintain motion when riding a bike? This is because you do not have a frictionless system. You do need to keep pedaling to overcome the force of friction between the tires and the surface of the road. Looks like he's popping a wheelie there. So yes, the law of inertia states no force is required to maintain the motion. However, you do have the outside forces present, that when she's popping the wheelie, there is friction between the tire and the road surface that you do need to overcome that force to maintain your motion. Letter N. Many automobile passengers suffer neck injuries when struck by cars from behind. How does Newton's first law of motion apply here, and what can be done to reduce these injuries? So if you're sitting in the vehicle, so sideways view, your head is here, and the headrest, and let's put a little neck on you there, and the rest of the seat here. Your headrest, many people don't put it in the right position. They tend to put it a little too low. They put it here as if at a stoplight. You can just rest your head, take a quick little snooze for a few seconds. You want to have it right at the back of your head. So if you are struck from behind, you were just sitting there, and you want to keep on sitting there. And you do keep on sitting there, but because you've been struck from behind, you're going to have the car, so the mechanism of the car is going to move forward, but your body is going to keep on sitting there, and so your head is going to be thrust backward. If that headrest isn't there to stop that violent motion of your head moving backward, it's going to go way too far back and then suddenly fall forward, and that is whiplash. And so your headrest allows for the situation where the vehicle, so you're in the vehicle, when you're struck from behind, that vehicle is going to move forward, you're going to keep sitting there, and as that headrest moves forward with the vehicle, that's going to prevent your head from being thrust backwards too quickly. So how does Newton's first law of motion apply here? Well, what applies here is the fact that the headrest allows for your body to continue in that sitting there motion safely while the vehicle moves forward. Now, what can be done to reduce these injuries? I think the number one thing is to make sure your headrest is properly positioned. And then the other option is, well, seatbelt your head to the chair. Probably not very a good recommendation, as visibility, your field of vision, one of the greatest tools you have in driving, would be very much limited. Hence, we have headrests. So make sure that your headrest is in a proper position so that you reduce those injuries. Final item on this page, letter O. If an elephant were chasing you, yes, I have no idea what an elephant would be chasing you. However, I do recall quite vividly when I first moved here how surprised I was to see news footage of people that were upset that they were at Yellowstone National Park. They were upset because bison came charging after them after they antagonized the wild animals of the bison, who are very massive as well. So perhaps I'm trying to protect you from being a less than intelligent tourist at national parks here. So back to the elephant. Not sure why one's chasing you, but hey, I'm trying to save your life. Its enormous 2,000 kilogram mass of the elephant would be quite threatening. But if you zigzagged, why would the elephant's mass now be to your advantage? So zigzagging, the strategy, the elephant has a large inertia. So if you take off running this way, the elephant coming charging after you might be successful. However, if you run a zigzag pattern, because that elephant has very much more mass, inertia, than you, it has a greater reluctance to change its motion. It requires more force to change its direction, change its motion. And fortunately for us, elephants have not taken geometry in learning that the straightest distance between 2 points is a straight line. They are going to keep their eye on the prize, which you happen to be the prize. And so they are going to follow your pattern. And so at each and every one of these turns, a change in velocity, it requires more force for them to change the direction than it does for you. So they're going to slow down with each and every change in velocity. So there you go, my friends. When you're being chased by a wild animal that hopefully you did not antagonize, zigzag might help you.